don't know. Am I going?
Yeah.
Is it happening?
Yeah.
It's happening. Okay. What's up, everybody? See, everyone online can't see this, but I mean, we got the entire university here behind the camera. Place is completely packed. I think it's not against. I think it's you shaking your head. Whatever. I'm just kidding. Actually, we do have. Oh my god, this is like 20 times more than most people I have, and there's only like 6. So, okay, we will start at 8:06. It's 8:02. So, do the math. 4 minutes. Let me get situated. Oh shoot, my mask. I need a bigger mask. My mouth is too big. Okay. So, yeah, this is the awkward first few minutes where I'm just lonely. Actually, no, but I have people here. Usually it's me in my room. What? I don't know. I'm a little more nervous now that there's actual people, but I'll be fine, I think. Well, there's only 3 now. It's kind of tough. I guess it's because I said, they're all going to come back, obviously. Right. Right. Wow, you guys really blowing up the live chat. Let's go. Usually there's no one in there. Wow, you guys got notebooks and stuff? Oh my god, this is so official. You can only call me Professor Arndt. No Steven. No, I'm just kidding. That's you said I. Wow. Wow. Need a haircut. Okay. Yeah, we'll start in. Welcome. What's up? Wow. Wow. Okay, we'll start soon. 7 people now. Wait, 7 people not in this room. Wait, we have 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 20, 30, 40, 50. Dang, we're really packed in here. Yeah. Okay, there's actually what? I should be able to do this math. 9 plus me, 10. I don't think I count though as a viewer, right? Oh, I know what I need to do. Oh my god, there's a lot of chat blowing up. Okay. All right, we will start in a couple seconds. I just need to pull up my notes. Maybe I shouldn't have said people can message me in the chat. This is a little distracting. I'll be fine though. I'll be fine. Okay. So, 1 sec. Okay. So, all right. So I will begin with. Now, I assume most of you. How many of you have actually taken the Putnam exam before? I assume 0, right? Oh boy. Okay. So I will begin with an introduction to what it is, what it's about, some of the history. Okay. This is, I'm going to do the whole shebang. Okay. So, God, I say that word. All right. So first off, the Putnam exam is the most prestigious mathematics competition for undergraduates in North America and arguably worldwide, although if you're not in North America, you can't take it, unfortunately. It began in 1938 with 163 students, and the competition has grown to include 4,500 undergraduate students and 500 competing institutions annually. Okay, so I'm going to explain some of the format of the exam. Now, the exam is, mark your calendars, okay, because it's kind of an all-day thing, all right? It's Saturday, December 4th, 2021. Always the first Saturday in December, unless there is a pandemic, in which case that doesn't apply. Well, I guess there is. Never mind. This year. All right. Saturday, December 4th. And actually, maybe they changed it with World War II. I don't know. Saturday, December 4th, 2021 is when the exam will be held this year. Can everyone hear me in the live chat? I assume so because I'm loud. Okay. So it consists of 2 3-hour sections. Okay. Each section is 6 problems and 10 points each. Okay. So you have the A section and the B section. Okay. So it's from 10 a.m. to 6 p.m. Okay. I guess I should do AM. Whatever. 10 a.m. to 6 p.m. The A section will be from 10 to 1. If I can just write numbers. So 10 to 1. And the B section is from 3 to 6. If you are on the East Coast, which I assume, we're on the East Coast, and I assume people there are on the East Coast, but if you're not on the East Coast, you might want to check that out. All right. So as you can see, you get a 2-hour break in between. Okay, the 2 sections. So each section is 6 problems, 10 points each. So A1 through A6. I bet that's not really visible, is it? No, that's, shoot. A1 through A6 and B1 through B6. And each problem is 10 points each. I'm not used to having a whiteboard this big, so it's taking me a while to write stuff. Okay, so 120 points total. If you couldn't figure that out, you might be in the wrong place. All right, so it's 120 points total, and it's taken by the 4,500 biggest math nerds in the country. Now, I think it's an understatement to say that the exam is hard, okay? What I mean by hard, I don't mean like as hard as, your Calc 2 final, okay? I don't mean as hard as the AMC 12, if you know what that is. What I mean by hard is this. So it's taken by the 4,500 biggest math nerds in the whole country. The median score out of 120 is usually 1 out of 120. 1 point out of 120 over 6 hours, okay? So the median, sometimes it's even 0. Usually that's the median score, okay? So if you take this exam and you get 1 out of 120, that puts you basically in the top half. So in some sense, that's really discouraging, but in another sense, it is encouraging because you know that everyone else is also dying. So usually if you get around, so the top 1,000, so it's out of 4,500. Is that visible? It's not great, but not terrible. So to get within the top 1,000, usually you need around 12 out of 120. To get in the top 500, or about top 10%, usually need around, something like 23 out of 120. Okay, and then skipping really far to get within the top 5. I'm gonna switch to blue. What's up? Hey. I'm gonna switch to blue. Okay. To get within the top 5, you need usually around a 100 out of 120. So this is like an 83%. This is like a B. Okay. You can get a B, then you're within the top 500, top 5 in the country. Now, of course, these change year to year, so you shouldn't completely bank on these, okay? But they're going to be roughly around this. So for example, in 2015, the top 500 cutoff was 13 out of 120 because the exam was really hard. And I learned that the hard way, and I did it for practice. And then, these, again, they change, but they're around this usually. So you should be shooting for these ranges, okay? So if you get a single point out of 120, that usually puts you around the halfway point, which is really good, especially if you're a freshman, it's your first time taking the exam. Top 1,000 also is obviously very good, and if you go within the top 500, then Dr. Hales will give you $500. Okay. Now that's a very hard $500 to make, so you shouldn't just study for the money because it probably won't end up well. Usually at Pitt, there's about 1 or 2 students who get this range. But of course, that's not an absolute, definitely. All right, so what makes it hard? Now, what makes it especially hard is that it relies more on problem solving than mathematical knowledge. So you certainly need to know a lot of math. You need to have, you basically need to have everything up to Calc 2 kind of like down, okay? But really what makes it really difficult is the problem solving component, okay? You're gonna be given a problem that you've never seen before, right? You're not given any direction, okay? And you have to figure it out completely from scratch by yourself. So this is kind of, in my opinion, this is kind of a pro. So, if you took an advanced, graduate course or something, that's not really going to help you, or it will only help you in the sense that it pushed you and made you, made you a better proofwriter and made you a better problem solver. The fact that you know this advanced theorem is not really going to help you. That knowledge is not necessarily going to help you, right? And this is really good, especially, like I said, if you're a freshman or a sophomore, you can still do very well in this exam, okay? So last year when I took it, I didn't even use any calculus. The first problem I used a little bit of number theory. The second was a bit of combinatorics, which I guess you don't necessarily get in your standard class. But the point is, you're probably not going to be using differential equations unless you're already among the top 50 in the country, for example, or top 100. All right, so why is it important? So it teaches you many different things, okay? So it teaches you how to maintain sustained, deep focus. It teaches you how to be a more creative problem solver. It teaches you how to be persistent when you are stuck, because absolutely you will get stuck. Every single person who's taking this exam has gotten stuck, okay? It teaches you how to synthesize, everything you have ever learned in math, okay? You have to synthesize it all together. And teaches you how to make a coherent argument. And a lot of these, although they are emphasized in your classes, will not be emphasized nearly at the same level, right? My math's kind of falling down, but it's okay. So they're not going to be emphasized, at nearly the same level as your standard math class. Okay, so why should you understand its importance? Why is it important to know it's important? The reason is that if you want to perform well, okay, and get the most out of it, you can be motivated by it, you must believe in it, okay? You must believe, all right? It's 6 hours long, okay? It's a difficult exam, okay? But if you really believe in, oh, that's really not visible, but 8 hours of fun, yeah. Sorry that's not visible, but it's just a big believe, okay? This isn't a religious class, okay? Just, if you want to perform well, right, and you want to, make sure you get through it, it's important that you understand why it is important. And I do firmly believe that it is. Personally, I've gotten more out of preparing for this competition than I have out of any of my math classes ever, I guess, including at Pitt, and possibly even all of them, okay? Because it sort of gives you something very different and something that's very important. But anyway, but yeah. So what I'll be doing today, that was a really long overview. Yeah, actually, that's the person in the chat said, I thought he was teaching math, not what Putnam is, SNH. Yeah, I was actually just about to say that. So yeah, I'm going to get to the math really quickly. So I'll be going over a problem and my process for solving it. This is going to be more of a light introduction to a lot of the techniques and stuff. In later sessions, I'll discuss them at a more more abstract level. But I just want to use an example first so that everyone gets kind of a feel for things. So I sent the problem in the email, and I'll give everyone few minutes to just look at it. If you've never seen it before and you solve it in 5 minutes, then that would be incredible. You'll definitely do well on this exam, but it's okay if you don't get it. So now the problem is, admittedly, very confusing looking. Okay, the language is very, so a big part of the problem is understanding what it's saying. So everyone should look up, here, wait. I don't know, like just look up 2005 Putnam problems, okay, and it's A2. And don't look at the solutions, obviously. So everyone look at it in like 5 to 10 minutes. I'll come back and I'll discuss the solution. Good luck. And you can also, if you don't want to do anything, then you can keep blowing up the chat and I'll look through it. Work on it. Just kidding. I know, I'm kidding. Everyone is able to find it, right? You just like look it up. 2005 Putnam problems, and then it's A2. Yes. A2 looks really fun, right? A2. I said it. I wonder if red is gonna. Oh, red's better? Yeah. Okay, good. Need to angle this. What? Wait, you just need to see that. There's so much lag. Yeah. So the red looks. Yeah. I'm waiting for the blue again.
I didn't do this in the chat.
Yeah. Okay, we'll go for like 3 more minutes. Again, if you haven't, it's fine if you don't figure it out. Obviously, it's hard. No. I catch myself. That's weird. Someone's showing me the stream, and it's, oh my god, that is really messing with me. It's, oh, sorry. It's like lagging, so it's weird. Okay, I think we should begin with the solution. Now, again, obviously, in a real practice or Putnam setting, you'd have like 3 hours to do this. Okay, but unfortunately, I don't think we have 3 hours tonight. So, I will discuss the solution, and in general, I will kind of give my some strategies and how you would go about Putnam problems in general. I just said in general twice. All right, so now I need to put this down. Okay, cool. So if I shot this up, no, definitely would not show. Okay. Okay. So the first thing you have to do with any Putnam problem, I mean, this is any math problem in general, but especially Putnam problems, is make sure that you read and understand what the problem is saying. Okay. This one especially is worded in a sort of like the wording and notation is very complex looking. Really, it's communicating kind of a simple idea, but of course they're going to make the questions like completely rigorous because it's taken by like a bunch of math nerds. Okay, like everyone's going to pick it apart, so it needs to be rock solid. So the first step is to read and understand what the problem is saying, and I mean that's kind of a hard step in itself, honestly. And it's important that you like really understand what it's saying in terms of like on a conceptual level, I guess. There's no reason to start solving a problem you don't understand yet. So that's the first step. So I'm gonna see. This is kind of weird because like the live doesn't see. Well, it's okay. So I'll just write. So read and understand problem. Okay. Now I'm presenting this as like 1, 2, 3, 4, 5, 6, 7, whatever. But you don't. It's like solving these problems is nonlinear, right? Like it does not follow in this kind of way. And I know that's sorry if that's really hard for the live to read. I'll bring this closer. So, okay, simple enough. Now the next step, and I will explain what it's saying, is to test small cases. Okay, make observations and search for patterns. Now this is like such an important strategy. Okay, and it's something that I would really recommend using very often. Okay, so you test small cases, and the reason that you do this, okay, and you make observations about what's going on, and really what you're trying to do is figure out what the pattern is, or what patterns exist, okay, and look for patterns. Now, oftentimes, especially with Putnam problems, these patterns are going to be subtle and hard to identify, and that's okay. I mean, that's kind of the whole reason it's hard. But a lot of times you will be tempted to jump into the problem for like, so this problem is about counting the number of paths for a general n. And you're going to be tempted to immediately try to like look at the general n and try to figure out what's going on. But really, it is almost always a better use of your time to pick a small case and analyze that. Pick a few small cases and analyze those. The observations or the patterns are going to reveal themselves much more quickly. Okay. All right. So that is something that will come up like all the time. Now, one thing I will say is like you don't want to make the cases too small. Like here, we wouldn't want to pick n equal to 1 because that's like kind of a degenerate case. And even something like n equal to 2 or 3 is not going to be that useful. So if the case is too small, then the pattern gets lost, right? So I decided when I at least solved this, I decided to use n equal to 5. Okay, so, and this is where also I'll explain what the problem is about. Another note about this problem, one of the reasons I picked this problem is because once I present the solution, you'll notice that really all it requires you to know is induction. Okay, so you need to know how to do induction. But there's like, in some sense, if you knew induction and you were like just a really smart ninth grader, you could still figure this out, right? It's not requiring like some theorem from differential equations to figure out. And that's sort of representative of how a lot of Putnam problems tend to go, at least the easier ones. The harder Putnam problems will require advanced knowledge, but they're so hard that like if you're anywhere close to them, you're obviously going to already know that. So anyway, so let's look at the board for n equal to 5. Okay, so now this is just going to be me drawing dots. Now, okay, so the goal is, so what is defined in this problem is something is called a rook tor. Okay, that's what's defined, and it's a path. It's essentially a path here. So this is the point 1, 1. This is the point 5, 1. Okay. Is that visible? Yeah, it's pretty visible. This is the point, 1, 3. It's just like it's a coordinate system. Okay. So each of these points has a coordinate. This is the point 5, but that's not really worth marking. And the goal is basically you control this here, this n. Okay, so you get a 3 by n grid, and a rook tor is a path that starts here in this bottom left corner. It goes through all the points once. Okay, and it ends here. Okay, and the goal is to figure out how many of these paths exist for a general n. Okay, so it's tricky. It's a tricky problem. So let me look at my work. So basically, the way that you want to proceed here is you just start drawing paths. You just try to make it work, right? And in this process, you're really trying to think about like what sort of patterns you notice or what observations you can make. Okay, so if you play around with this a little bit, so and again, I need to, so maybe I do something like this. Okay, now like it's kind of a random process a little bit, but see, I'm trying to. I don't exactly know what I did to find the first observation that's important, but like let's say you do something like this. So something like this, for example, is now when I was solving the problem, again, I don't exactly remember how I went about just doing the paths, but one thing you should notice from this is, you need to cover every point. This point here can no longer be, actually wait. Yeah, this point here is can no longer be like accessed, for example, okay? Because if I'm here, right? So this point can only be accessed from these 2 points, okay? Because you can only access adjacent points. That's something I should have explained as well. So this point can only be reached from this one or this one, and we've already covered these, and like it can't really be accessed from this one because it's 5, 1, right? And that's the end. That's the ending. We need to end there. So if I'm in this situation, I need to go here, but then I'm screwed because then I need to go here, and I haven't covered all the points. So that's like an example of something that you may notice. Really, the key idea with that, the observation is that, once you've every point has only a few points that, like for example, so this point here can be reached from these 4, right? The 4 adjacent points, and you have to go in and out, right? And you can only go in and out through one of those 4. And but the points in the corners, for example, so this one is a special case, but like this point, for example, can only be reached from these 2, right? So it's very limited. Like the path through this point is very constrained. And in general, whenever you have a situation, whenever you have a really constrained situation, that's going to help you figure out characteristics of something, because if something's really constrained, then there's only 1 or 2 ways that you can make it happen, and you can kind of fill in the details in between, right? So in particular, this point here can only be reached from these 2, right? So if I'm at this point, right? So if I have some path to this point, then I 100% need to go here and then here, for example. Okay, I need to do that. Or if I'm now here, this is actually where I can introduce the next observation. So the first one is that different points, each point only has a few other points of access for this path. So the second is now either I go in and out like this, so I go in and out, or I have to go in this way and out like that. Okay, so I have to go in and then out. But basically, the big idea is you need to once you get here, you need to do that corner like that. Now, this is where the second kind of really important observation revealed itself. Okay, at least I was kind of thinking about it, revealed itself to me. Now, this path here, right? What is wrong with this path? Who can explain to me? Is that visible on the street? Yeah, it is. Who can explain to me what's wrong with this picture? So I'm here, right? Who can explain what's wrong? Yeah.
Any other path to make would go through a point again.
Exactly, right? So I can't get out of here, right? So what's happened is I constructed a wall here. I constructed a wall, and I can't get past that wall, right? Because you can only go through each point once. So the next big idea, right? So this whole wall idea, okay, is going to become very relevant. So you can't make a wall vertically and leave points behind. So what that means is you need to, like, any path. So like if I had some path like let's say I had some path that was like this, right? Absolutely, this cannot work. Okay, because here with. Okay, so it's getting kind of messy, but I think you can still see it. So I'm here now. This cannot work. The reason is because at this point, I need to go on one side of the wall or the other, right? I still need to cover these points. So if I go to this side of the wall, well, now I can't get over, right, and cover these. But if I go to this side of the wall, then I can't get over here and cover these, right? So these walls, they split the graph in half, and they don't let you cover all the points like you want to, okay? The only way what that means is that obviously you need to cover all the points, so you need to like make all these walls, right? But you need to do them in succession. So for example, right, I need to cover like the first wall first, then the second, then the third, then the fourth, and the fifth, in that order, right? Because if I cover, for example, if I have some path which covers the fourth wall before the third, then there's some point in the third that is split in half, right? So an example path might look like this. Okay, so here, right, I have to cover the first wall first, so I've gotten these 3 points. Then the second wall, and then the third. Okay, like that. Again, I'm going a little fast because, well, if you guys didn't have a lot of time to spend with this problem, I did. So that's an important idea. And if, like I said, let's use an example. So let's say, it could be anything, right? Where, let's say I did something like this, right? I completely screwed it at this point because now I have this wall at x equal to 4, and I can't, if I move to one side or the other, then I can't get across it, right? So I need to do all of these walls in succession. All right, so okay, so that was kind of step 3. So what I did was I tried drawing paths. Eventually at some point I drew this path or something similar, and I realized, wait a second, I can't make this work, and this is why. And then I continued that sort of downward. Okay, so I guess this was kind of step 3, which is step 3 is to, and again, it's not 1, 2, 3. This is just kind of, I'm organizing it in that way. So you kind of think of key observations. You also want to have, in general, it's good to have some kind of a key strategy. So how are you actually going to solve this problem? So at least that's a little harder to notice. When I first looked at this problem, well, actually, I guess I can explain. I can explain like where I thought of this. So the strategy to solve this problem, it's getting messy. Okay. So let's say, for example, so you could have a path like this, right? And then I'm here, and I have to go here, right? Now, at this point, if you actually look at this situation, what you have is like a completely fresh board, okay, 4 by 3, but I'm starting in the top left corner, right? You could also, maybe I have a situation like this, right? And here, I actually have if you look at what I have left to do, I have a completely fresh board, but I'm starting in the top left corner. It's 3 by 3, right? So what that kind of prompted me to do is think about recursion, okay, to try to solve this recursively. And you can also get that from the fact that computing an exact formula for something like this already appears difficult. And if you can't compute an exact formula for something, usually recursion is a good way to go, right? So, but the recursion also comes through when you're drawing paths. Like, if I am working and I draw this path, and I see that, okay, this is just the 3 by 3 case, then I can know that later down the road I can reduce it to that case. And presumably, if I'm able to solve, the case for n equal to 5, I am also able to solve n equals to 3 beforehand, right? So anyway, big idea. The key strategy here is recursion, and the observations are the whole wall thing, and also like there's limited accessibility for each point, right? So when you're at a point, you only have a couple decisions you can make, even though it appears like there's a ton, right? All right, so kind of beating around the bush. Well, no, this is how it's supposed to go. So now what I'm going to do. So what I'm going to do now, what I noticed, one of the problems with this recursive approach is that if I want to use it, I need to figure out a way to compute the number of paths from the top left corner to the bottom right corner. So this is a different quantity, right? It's very similar, but you may think, oh, this is doubling my work, but not necessarily, because if you get a system of equations or they are related in some way, then solving one can help you solve the other. So what I'm going to do is define an. Yeah, okay, you can see on the right. So an is the number of paths from 1, 1 to n1. Okay, so this is what we want. A5 is what we were working to compute. Bn will be the number of paths from 1, 3 to n1. Okay, so the top left corner to n1, and this is sort of the secondary thing that we're using to help ourselves. Okay, so now let's with these observations in mind, let's start developing these formulas, okay? Or start, now we have a better sense of direction when it comes to how we're constructing these paths, okay? So let's just casework, okay? So let's just casework. We start here, right? There's two things we could do, okay? Either we go up or we go to the right, right? Now, if we go up here, right, we know that we have to go up to here, right? Because we talked about this. So we talked about the fact that if, this point only has 2 points of access. So if we went instead to the right here, then there's only one way that you can get to this point. You can't get out, right? So you can only go in, you can't go out. So we know, and this is literally just process of elimination, right? We go, so from here we have to go up, and then from here we can go either right or up, but right is problematic for the reason I explained, so we have to go up. And then from here there's only one choice, we have to go to the right. Okay, so any path which starts with going up has to do this. And this here reduces to B4. Right, does everyone see that? Because it's a 4x3 board, we're starting in the top left corner. So this reduces to B4. Okay, so what we have is A5. So the total number of paths is equal to B4, and then plus the other case. Okay. Now, let's say we went to the right. Okay. Then from here, we could go up or to the right. Right, so this also splits into two cases. Let's say we go to the right, we could go up or to the right. So basically the idea is what we can do is we can, for any path, and this is kind of, I guess, I don't know if this is a conceptual jump, but like, oh, it's 9:46. It's okay, I'll be done. Wait. Oh no, they haven't changed the clock. I was like, okay. So the idea is that we can characterize every path by when we decide to turn up. Okay, turn. Okay, turn up. Yeah. Okay. So we can either go up right away, we can go right up, we can go right up, we can go right up, right? And that gives us all the paths, right? So let's say that we go right up. Now the idea is in general, right? We're thinking about the general proof, right? Because that's what we need to do. In general, we'll say, okay, we take k steps to the right and 1 step up. K can be anything from 0 to n-1 or something like that. Now in this case, let's analyze what we have to do. Now we have 3 options, right? 3 options. We can't go here for the reason I explained before, because if we go here, we could create a wall, right? So that one's ruled out. Now we also can't go here, all right? And I guess, well, let me use quickly just change the case a little bit. So we go up. We can't go here because that makes a wall. We can't go here because if we go here, this point, right? Well, actually, let me think. Oh, no. The problem with going here, sorry, I'm getting confused a little bit. All right, so we can't go here. Now, there's a reason that, oh, yeah, so, let me think about it. So I have to think about this a little bit. So we can't go here because that creates a wall. So that gives us these 2 options. Now there's a reason that we can't go here.
I'm sure you wouldn't be able to go to any of the adjacent points.
Like you mean which points?
If you went to that new point, then you can't go up, you can't go right, you can't go down. Because you make a wall.
Oh, I see. Yeah, so you can't, right. So here you can't go. So if you went here, you'd be screwed because you make a wall, right? So you make a wall this way because you split it into 2 sections. If you go to the right, then you also sort of sever the graph, right, into 2 sections. And if you went down, well, see, I'm trying to think of the general case, which is why I'm confusing myself a little bit.
So you just build the other corner first before you do that. Like you have the 2 corner, right?
Yeah.
So you're forced to either 2 choice there, and then you wrap up, and then you have to go to the corner. Therefore, you always have 2 corners at the end, and then just calculate the 3x3 in the middle.
So you're saying are you saying that you have to do this? Is that what you're saying, or no?
No, just saying, just have the corner first, right?
Oh, okay.
Yeah, just build the corner first.
Yeah.
And then just mind the amount of path that the 3x3 middle goes in.
Right. So what should we do here? So we should go. So we're going up as the case. So you're saying we should go which way?
You have to go left.
You have to go left, right? Right. So again, I will get back to it if I can remember, but there's a more formal reason you can't go here. But basically, you have three options. This one's ruled out. This one's ruled out. You have to go to the left. Okay. Yeah.
You can't go past that point, like, point out.
You can't go past this point.
Yeah, no, if you go that way, you can't go up and then back that way without creating a wall.
Oh, I see what you're saying. Yes. Right. Okay. So in general, yeah. Thank you. So in general, if you go this way, then you can't. Okay. Yes. So if you go this way, then you can't get back to here without making a wall, like you said. Right. So if you go this way, you can't get back here. Right. So you have to go this way. Okay. Now here, right, we have two options. This one makes a wall, so we have to go this way. Here we only have one option. We have one option. And then here we have one option. And here we have one option. Okay? So we make this snake. Okay? We have to make this snake. And the way that you prove that is, like you kind of prove that through casework. And I mean, that's sort of not always, that's going to be maybe a lengthy proof, but that's, you have 3 hours. Okay? Is all I'm trying to say. Like you can take the time to write a long proof. So here, now let's make sure that this holds up in general. So n equals to 5 might be getting a little too small here, but, well, okay, the point is that if you do this, then when you get to here, it reduces to B2, okay, because you have a fresh, like, rectangular board at the end, right? So let's say, so in general, right, you would say, okay, this is the case you're analyzing in general, this is some arbitrary K, right? When you're at this point, you have 3 options. You explain why you can't go here, you explain why you can't go here, right? So then you're forced to go here. At this point, right, and at every point in succession, you can never go up because that makes a wall, right? So you always have to go left. You always have to go left. And then from here, you only have one option till the very end, right? So that's the idea, okay? So what that means is, oh, this is kind of slow. Now what that means is we can get a formula for A5 and in general a formula for AN because we thought in general terms. So yes, it's getting messy. That's okay. So if we go up to the right, that's B4, right? So if we do this, that's B4, okay? Because we're in the top left corner, we have to get, it's N is 4 and the height is 3. Now, if we decide to go like this, then we have to do one of these snake things. And then this board here is B3, right? Now, if we do, instead we go like this, right? That's B2. Is that visible in here? If we go here, right? You can see where this is going. This is B1. Okay, kind of a weird case, but still defined. And obviously, we can't go all the way to 5-1 because then that wouldn't make sense because we have to cover all the points. Oh, it's 8:50. Okay, I'll get to the point. So this is the formula, right? And also, like, so the formula is basically AN is the sum of, So is the sum, my sum is terrible, but K equals to 1 to N minus 1 of B sub K. This is the formula. Okay, so you're adding all of the smaller b's. Now we need to figure out what a formula for B, right? So we need to figure out a formula for B. Now it's going to be basically the same, and I'm going to kind of gloss over it. But it's going, the same sort of logic applies. There's a small kink, which is that you end up getting Bn is 1 plus the sum from K equal to 1 to N minus 1 of AK. Okay, so there's an extra 1 plus, and that has to do with the edge case when N equals 1, basically, because B1, when N equals 1, B1 is defined, but A1 is like still 0. So anyway, again, I'm glossing over this. You'd have to look into yourself. So you get these two formulas. Now again, I mean, these two formulas are kind of cryptic, at least. They might look a little cryptic. So what we're going to do here is test small cases. So what I'm going to do is compute small values of an and bn and see if I can find a pattern, right? So we're kind of going back to the beginning of what we did. So now we can erase the board because we have formulas. So here, first the base cases, right? So if you have is that even visible at all? Okay, so if n equals 1, right? We know that a1 is 0 because if we start here and end here, like we don't have a path, and b1 equals 1 because we just go straight down. Okay, those are the base cases. Now from that, you have a1 equal to 0, b1 equal to 1. So now a2 equals, look at the formula, a2 just equals b1. So a2 equals 1, b2 equals this plus 1, which is 2. Okay? A3 equals, the sum of these two, so 3. B3 equals the sum of all of these plus 1, right, which is 5. I hope that this is, oh boy, I hope this is correct. Okay, so 8 and B4. Oh wait, yeah, I did that right. Wait, sorry, I think I did it wrong. So it should be that you add, so A1 is 0, B1 is 1, then A2 equals 1, B2 equals, so B2 is just, sorry. So remember, you only add up to n minus 1, right? So this is just so you only do, so A2 equals B1, B2 equals A1 plus 1, because you only sum up to n minus 1, right? So this is just 1. Then A3 equals B1 plus B2, and B3 equals this plus 1, just 2, right? A4 equals this plus this is 4. B4, this plus 1, all these plus 1 is 4. A5 equals all these. B5 equals all these plus 1. Okay? So notice, what's the pattern?
Exponential growth.
Yes, exponential growth, powers of 2, right? So our conjecture is that these will always double, right? These will always double. And see, the great thing about this method, right, is that this is kind of crude, right? Like you could figure this out by just looking at the formulas, but this is so much easier to figure out what the pattern is. And then you can make the conjecture for what you think the answer is, and you can work from there. So our conjecture specifically, right, the conjecture is that an equals 2 to the n minus 2, okay, for n greater than or equal to 2. And then, so for n greater than or equal to 2, okay, and then for n equal to 1, you know a1 is 0, okay. And if you write that, this is really messy probably on the stream. Yeah, okay. If you write that, that is the correct answer. That's the correct formula. The way you go about proving that is you can use induction, right? So really all the induction proof isn't too bad. And one of the reasons is like, if you actually look at this a little bit more, what you realize is that here, B3 plus B2 plus B1 is just A4, okay? So you can actually rewrite this recursion in a much more compact way. Again, I'm rushing, I apologize. So you can actually write it like that, okay? So in general, you have an equals bn minus 1 plus bn minus 2, bn minus 3, but all the bn minus 2, bn minus 3, etc., all of those are just an minus 1. So you end up getting this recursion for A, which is very clean. And then for B, you end up getting the recursion. So let me replace this with n's. Okay. Again, super messy, I apologize, but bn, you end up getting 1 plus, well, actually, you can write it in the same way. So you pull out the biggest A term, that's an minus 1. The rest of it is just going to be bn minus 1. Okay, so you can get that recursion for that. Okay, And you can obviously tell they are equal to each other. And then once they become equal to each other, then the power of 2 thing comes right out for the induction. Okay, so that was kind of fast. Now what's good is that you can prove this conjecture without doing that simplification. It makes your proof a lot easier to write if you do this. But you can kind of just tackle it and you can get it from the original formula. Okay. Now writing the proof. Okay, so I'm not going to write the proof here. Writing the proof is a major part of the problem. Okay, absolutely. And people usually, or at least I usually, tend to underestimate how long the proof may take to write or how confusing the proof may be to write. So even though you may have fully solved the problem, like you know the answer and you have a really good explanation, writing the proof is a whole different game, basically, because you need to be very rigorous. Well, I mean, you don't need to be super rigorous. You just need to give a very airtight explanation. Okay, so never, rush the proof. Okay, in this case especially, the proof is going to has potential to get very messy because if you have like an algebra problem, you're just doing some simplification or like an integral or something, then the proof is really easy. You just do the integral. Okay. In this case, there's a lot of exposition. There's a lot of, we go here, so then we have 3 cases, and then we have to go here, but then you roll up the cases. So if you're not careful, your explanation will become very long and unwieldy, and you'll miss something. So one of the best ways to organize your stuff is to write lemmas. Okay, so a lemma is like a mini theorem that you write in your proof. Okay, so what you do with the lemma. So let me use an example. Well, actually, no, I can explain that example. So let's say you have some intermediate results in your proof that you want to use to cite. Then at the very beginning of the proof, you can write the lemma, which is this mini theorem. And then later in your actual proof, you can invoke the lemma. Okay, so you can just say, according to the lemma, which I already proved, this must be true. This really organizes this stuff, okay? Because if you don't organize it in this way, then every time you get to an intermediate result, like a whole other sub-proof that you need to do, you need to write it out, and it gets super messy. Oh, sorry. Yes, it's 9 o'clock. Okay, I'll be done in like 2 minutes. Okay, well, that might be a lot, maybe 3. Okay, so as an exercise, take the time to write the proof. That could be a good exercise. Now, what I recommend as a lemma is you make a lemma something like the snake pattern lemma, okay? Something like this, which basically says, so the lemma is basically like, if you go to the right this many and up 1, then you must go through this path, right? So you make that a lemma, and then later in the actual proof, you can invoke that and it organizes it more nicely, right? This also, if you're like a pure science nerd, you can also think of this like a method, okay? Yeah, you can also think of this like a method, and maybe the proof is like main. That's a very Java way to say it, but anyway. All right, so lastly, reviewing, okay? So when you review a problem, or after you solve the problem, okay, you need to review it. And the review process is usually, so the review process is very involved, okay? And there's many layers of depth to it, okay? So for the sake of time, I'm just gonna touch on a couple layers. So the first, when you're reviewing a problem, the first layer is understanding. So you need to, when you're looking at solutions, right? And actually the solution I presented here is not really a posted solution, just because the posted solutions are like very quick and compact, but also like impossible to actually think of. So, but anyway, when you're reviewing solutions, you need to understand every step of the solution. You need to understand why every step logically follows, right? And how it works, okay? That's the first layer. The second layer has to do with motivation. Now, I don't mean motivation like motivation to go to the gym or whatever. What I mean is, not only do you need to understand the steps of a proof, but you need to be able to understand how someone would actually think of those steps, okay? Like, people don't just pull these out of thin air, all right? There's reasons, there's cues in the problem. There's cues in the problem that tell you what, what to do, okay? So when you see a solution, someone is going to present it like the answer is this, powers of 2. And they're not going to explain how they actually got that. And this is something you need to figure out yourself, and it's usually very hard to actually figure out, okay? But it's super important because in the exam, you need to be able to understand like the problem solving process, right? And the last layer, after you've done all that, is mental change. So you need to be able to basically at the end, you think about what things that, when you were solving the problem, what things did you do right? Maybe what things did you do wrong? And that means this is very like abstract. It doesn't mean like, oh, I did. Like sometimes you may pursue an incorrect path, but that path actually made logical sense in the moment to pursue. So it's not just something you did wrong, right? So mental changes, you think about, okay, what did I do wrong, right? How can I change how I approach these things to improve for the future? So the review process is very long, and I'll probably talk about it in depth, like much, in a later session. Okay, so this is a paraphrase from a previous stream I did. Okay, so you might spend like 8 to 10 hours in total on a problem. Okay, or at least what I did when I was doing some of the hard ones. But really, what you're doing, the reason that you do that is you're digging deeper and deeper, and you're trying to find the big ideas that you can apply in general. Okay, so this problem, you're not going to see this problem on Putnam, right? But you're going to see a lot of the big ideas. And in order to actually figure out those big ideas, you need to really dig deeper and deeper and spend a lot of time with the problem to find them. And so in a future session, I'll be going over many of those. But yeah, okay. So hopefully this was helpful. This gave you an idea of what Putnam problems are like. I will hold 2 more sessions, most likely 2, before the exam date. So be on the lookout for those in your email and stuff. As for now, if you ask me what to do to study, I will tell you to just work on previous Putnam problems. Specifically, you should focus on A1s, A2s, B1s, and B2s, okay? So don't be touching into the A5 and, B6 range, whatever, okay? Those are like basically impossible. Usually like 5 people in the entire country will solve them, okay? So this is the best way, focusing on these numbers. Now, again, even A1 is very hard, okay? Half the people only get 10% on this, okay? Only get 1 out of 10 points. So yeah, don't get discouraged. All right.
Is that the order of increasing difficulty? Like is B1 harder than A1?
So in general, the B section is a little harder than the A section. B1 and usually A2 and B1 will be about the same difficulty. But again, it's completely subjective to what you know, right? And what you're able to actually figure out. It kind of depends on the day, Chat. Oh, thank you for the chat. All right. So as always, make sure to smash like and subscribe. Okay, I had to include that. All right. And I will see you in a couple weeks. Thank you, everybody, for coming.